Imagine you run a distributed cache with 100 servers. Everything is working perfectly. Then traffic grows, so you add just one more server. Simple enough, right? Wrong. Suddenly, your cache hit rate crashes. Database load explodes. Latency will shoot up, and your entire system starts lagging. All because you added a single server. Sounds crazy, right? Today, you will understand why this happens and how companies like Amazon, Netflix, and Redis solve this using one of the most important concepts in distributed systems, that is, consistent hashing. Let's start with a very naive approach. Suppose we decide which server stores which key using a simple formula, that is the modulus of 4, where 4 is the number of servers that I have. A user profile might go to server 1, a product might go to server 3, and everything looks balanced. But here is the problem. What happens when we add a fifth server? Now, my formula will divide the modulus with 5. Almost every key gets assigned to a different server. The mapping changes completely. A key that was previously assigned to be on server 0 may go to some other server too. In fact, nearly all keys got distributed, and that is a disaster. Imagine a cache cluster storing millions of objects. All those cache objects are already using on specific servers. Now because the mapping changed, requests that go to new servers, but those servers does not have the cache data. So every request becomes a cache miss, and this phenomena is called the cache storm, and the chain reaction looks like this. So first the cache hit will decrease, database load will increase, database response time will increase, and latency will increase, and ultimately the user will start experiencing the lag and will start complaining and all those stuff. All because you added one single server. So the question becomes, can we design a hashing mechanism where adding or removing servers causing only a fraction of change? That's exactly what consistent hashing solved. The key idea is simple. When the number of increase in the server is from 1 to 2, we don't want all keys to move. We want only a small portion to move. With consistent hashing, when a server is removed or added, only about 1 by n keys remapped, not almost all of them. In other words, the amount of redistribution is proportional to change in the number of servers, not proportional to the total number of keys, and that is a huge win. Now, to understand how this works, let's build it step by step. Suppose we use a hash function like SHA, which gives me values in the range of 0 to 2 to the power 160. Now this range is what we call the hash space. Imagine these spaces are distributed not on a straight line but on a ring. We bend it like a circle, and this circle is called hash ring as shown in this diagram. Think of it as a giant clock. The end connects back to the beginning. Now we want to hash every server request and along with the server IDs. So let's say my server A is on position X, server 1 is on position Y, and so on. Each server get placed somewhere on the ring. Now we hash the every request or key. User profile, product, session, everyone will be mapped somewhere in the ring. Now comes the magic rule. For any key, move clockwise around the ring. So we move, let's say we pick this green color ring and we start moving clockwise. We encounter S1 server first. So ultimately this key will be mapped to server 1. So whenever a server 1, let's say session request goes to the load balancer, the load balancer will map it to the server 1. So the key belongs to server 1. Suppose we add a new server, let's say server D, right? Now adding this server will give me the minimal distribution. So I added this server 4. So only the keys that fall between server D and predecessor, let's say server 2, they would be redistributed, right? Other key remains exactly where it was. So instead of moving millions of keys, we only move a small fraction. And that's what we call the minimal redistribution. And that's why this consistent hashing is so powerful. Now at this point you might think we are done. Not quite. That's the major issue. Servers are randomly placed on the ring, right? This means partitions might mean the difference between the positions of the two servers can be uneven. And one server might owns a tiny slice, right? The server 1 owns a very small, but the server 2 holds a large part of the ring. So as a result, some servers were handled significantly more traffic than the others, and this is not ideal, right? Another problem, uneven key distribution. One server may end up storing much larger keys. Let's say one server is storing 10 million objects while another is storing only 2 million. Now one machine becomes overloaded while others sit idle. So how do real systems fix this? They fix this using virtual nodes. So a virtual node is simply a logical representation of a physical server. So what I mean is, instead of placing a server only once in the ring, what we do is we place it many times. Server A appear at most as 500 positions. So these are just the virtual positions. We are not doing the copy of actual server. We are just defining or copying its the positions on the ring. So server A might be at 100 positions, server B might be at 500 positions, and all these positions still point to the same physical machine, right? So in large scale production systems, a server can have thousands or even millions of virtual nodes. So how do engineers know whether the distribution is good or bad? One simple concept is standard deviation. A lower standard deviation means more balanced partitions, more balanced traffic, and more balanced storage. So, in short, lower deviation equals healthy clusters. But there is a trade off. More virtual improves the balance, right? But they also increase memory consumption, like metadata storage, ring management. So, engineers must find the sweet spot. Not too few, not too many. As we now let's discuss another critical concept. What happens if the server dies? Suppose a key exists only on the one server. Now that server crashes. Okay. The next request becomes a cache miss because the key is gone. Potentially millions of cache misses. So, to prevent this, distributed systems use replication. So, how replication works? Instead of storing key on one server, we store it on multiple servers. And this is called controlled using factor called replication factor. If R is equal to 3, every key is stored on 3 different servers. And 3 different servers mean do not store them on the virtual nodes. For each server, we store it only on one virtual node. And when placing the replicas, we move clockwise on the ring and pick the next distinct server. Notice the word distinct clearly. We do not store replicas on multiple virtual nodes. That would defect the purpose. We always choose different physical server. So a replication factor of R allows the system to survive. R minus 1 simultaneous server failures for any particular key. For example, replication factor is equals to 3. The system can tolerate 2 server failures and still serve the data. Now, A common interview question is, what is the difference between virtual nodes and replication? Here's the easiest way to remember it. Virtual nodes solve load balancing. Replication solves fault tolerance. So virtual node answer, how evenly is my data distributed? Replication answers, how many copies survive if machines fail? In real world, system uses both together. So one cannot go without the other. Now, let's recap everything. Simple hashing causes massive redistribution, right? So we use consistent hashing, which helps servers and keys on the hash ring. Adding or removing a server affects only a small portion of keys. Virtual nodes improve the latency, replication improves the fault tolerance, and together these ideas power some of the largest systems on the earth. The next time someone asks, why do we use consistent hashing? You will know the answer, isn't it? It's about scalability, availability, reliability, and surviving change without bringing them the entire system. If this explanation helped you understand the consistent hashing, hit like and subscribe and let me know which distribution topic should I cover in the next video.